We discussed the third case in integrals involving rational functions by partial fraction. Case 3 is all about distinct quadratic factors. So, for each distinct quadratic factor in the form ax squared plus bx plus c that appears in the denominator of a proper rational function, there will be one partial fraction corresponding to it, and it takes the form a times the quantity 2ax plus b plus b all over ax squared plus bx plus c. A and b are constants to be determined. Now, in algebra, the partial fraction corresponding to ax squared plus bx plus c is given in the form ax plus b all over ax squared plus bx plus c. So in here, we're doing some modification. No? So we deviate from the usual form given in algebra. Instead of ax plus b in the numerator, we will be using a times the quantity 2ax plus b plus b. What is special about 2ax plus b is that it is the exact differential of the denominator. So if we take the differential of ax squared plus bx plus c, we will be getting 2ax plus b dx. So once we have come to that point wherein we are to evaluate the integral of a times 2ax plus b all over the quadratic factor, it will take the form du all over u. Whereas, if we stick to the form given in algebra as ax plus b all over ax squared plus bx plus c, once we have the values of a and b, we still have to complete the differential of the denominator. So we will be skipping that part if we will use the other form as given. No? A times the quantity 2ax plus b plus b. So as before, we will be calculating for the values of the constants a and b. Another thing that you should have noticed in the partial fraction corresponding to this quadratic factor is that there are two constants to be determined for one partial fraction. Okay? And that is logical. Why? Because the degree of the denominator is 2. And for it to be a rational function or proper rational function, the degree of the numerator is 1 degree or 1 degree less than the degree of the denominator. No? Or at most, the degree of the numerator should be 1 degree less than that of the denominator. Since the degree of the denominator is quadratic, meaning it is of power 2, then the numerator will be 1 degree less or linear. So let us have an example. Let us evaluate the integral of x dx all over the quantity x plus 1 times x squared plus 4. Before we work on this, the quadratic factor ax squared plus bx plus c should be such that it is no longer factorable into linear factors. Example is x squared plus 4x plus 5. Though it is quadratic in form, it is factorable into two linear factors, or let me change that. The constant here should be 3. Okay, so x squared plus 4x plus 3. It is factorable into x plus 1 and x plus 3. So when we speak of the quadratic factor ax squared plus bx plus b, it must be such that it is no longer factorable into linear factors. Okay? Because if it is factorable, then it will fall under either case 1 or case 2, wherein we have a linear factor, either distinct or repeated. Okay? So in our example here, x squared plus 4 is essentially quadratic because it is no longer factorable into linear factors. So just like what we have done before, We will isolate the integrand. We isolate the integrand and rewrite this as a sum of partial fractions. So x all over x plus 1, x squared plus 4. So the denominator is already presented in the factored form. X plus 1 is linear and x squared plus 4 is quadratic. So there will be one partial fraction corresponding to the linear factor x plus 1. And we shall write it as a all over x plus 1. Plus, for the quadratic factor x squared plus 4, it will be b times, we take on the derivative of x squared plus 4, which is 2x, plus another constant c all over x squared plus 4. So combining these two fractions and then canceling out the denominators, we'll be getting x equal to a times x squared plus 4 plus b times 2x times x plus 1 plus c times x plus 1. So let us write the right term in the expanded form. Ax squared plus 4a plus 2bx squared plus 2bx plus cx plus 1. We collect similar terms. So we have a plus 2b times x squared plus 2b plus c times x plus 4a plus c. So this is supposed to be c. Right? And then we compare coefficients. We can start at x squared. So the left side, the coefficient of x squared at 0. At the right side, it is a plus 2b. The coefficient of x at the left is 1. At the right side, it is 2b plus c. And then the constant at the left is 0. At the right is 4a plus c. Alright? So, we can solve for a, which is equal to negative 2b. Alright? A is equal to negative 2b. And so let us substitute it to the third equation. 0 equal to 4 times negative 2b plus c. That will be equal to negative 8b plus c. So let us call this as equations 1, 2, and then 3. Alright? We can add or we can subtract 3 from 2. We can subtract 3 from 2. So 2 minus 3. 1 minus 0 is 1. 2b minus negative 8b is 10b. C minus c is 0. So b is 1 over 10. Okay? Let us rewrite it clearly. That will be equal to 10b. Right? Now that we have the value of b, we can solve for a in equation 1. A is negative 2b, so that will be negative 2 over 10. Okay, or negative 1/5. So that is the value of a. And then for c, well, we can substitute it to equation 3. The value of b to equation 3. So what do we have? 0 equal to negative 8 over 10 plus c. So our c here will be positive 4/5. There. So going back to our integral, we rewrite our integrand as a negative 1 over 5 over x plus b 1 over 10 times 2x over x squared plus 4. I am rewriting the other partial fraction into two fractions now. And then c is 4 over 5 all over x squared plus 4 quantity dx. So the integral of negative 1/5 over x dx is negative 1/5 ln of the absolute value of x plus, we go to the second integral, it will be 1 over 10, and 2x dx over x squared plus 4, as mentioned before, will take the form du over u, whose integral is ln of x squared plus 4, plus 4 pips. The third integral has a denominator in the form a squared plus u squared. So du over a squared plus u squared will yield the arctangent function. And since our a squared is 4, that means that a is 2. The answer is 1/2 arctangent of x all over 2 plus c. Alright, so let us combine the first two terms involving ln. I can factor 1 over 10. So that becomes negative 2 ln of x plus ln of x squared plus 4. Okay, plus 4 over 10 is 2 pips, arctangent of x over 2 plus c. So let me move this a little to the left. Okay, same as this one. Okay, so this should be plus c and plus c. So 1 over 10 ln of, that becomes x squared plus 4 over, because of minus, ln x squared. 2 becomes the exponent of x, so it becomes x squared plus 2 pips arctangent of x over 2 plus c. Another one, integral of x squared minus x plus 2 dx all over x squared plus 2x plus 5. X squared minus x plus 2 all over x squared plus 2x plus 5 is quadratic. So the denominator is again a combination of a linear factor x and a quadratic factor x squared plus 2x plus 5. So one partial fraction for the factor x and another for the quadratic factor. So it will be b times, we take the derivative of x squared plus 2x, which is 2x plus 2, plus another constant c all over x squared plus 2x plus 5. So we combine again the fractions and eliminate or cancel out the denominators. So a x squared plus 2x plus 5 plus bx 2x plus 2 plus cx. So we'll combine similar terms, ax squared and 2b x squared. Then 2ax plus 2bx plus c. Okay, we factor the x, and then the constant is 5a. So x squared minus x plus 2. Alright, so we compare coefficients. X squared 1 is equal to a plus 2b. X raised to 1 is negative 1. 2a plus 2b plus c. And the constant 2 is equal to 5a. So from the third equation, it will lead us to the value of a equal to 2 pips. And if a is 2 pips, we can calculate for b. So 1 equal to 2 pips plus 2b. That will be 1 minus 2 pips is 3 pips equal to 2b. So our b is 3 over 10. Okay. And then, how about the value of c? So let us substitute it here. Negative 1 equal to, negative 1 equal to 2a. So 2 times 2 pips is 4 pips. Plus 2b. 2 times 3 over 10. That will be 3 pips. Plus c. So 4 pips and 3 pips is 7 pips. Negative 1 minus 7 pips equal to c. That will be negative 12 over 5. So c is negative 12 over 5. So plug in these values to the partial fractions. We have the integral of a, 2 pips over x, and then b is 3 over 10 times 2x plus 2 all over x squared plus 2x plus 5 plus c, negative 12 over 5 over x squared plus 2x plus 5 quantity dx. So I think I should write this down below. Here. Okay. So integrating 2 pips over x dx is 2 pips ln absolute value of x plus 3 over 10. Again, this part takes the form du all over u. And the answer there is ln absolute value of x squared plus 2x plus 5 minus 12 over 5. Let us now integrate this dx over x squared plus 2x plus 5. We shall write this as x squared plus 2x plus 1 plus 4. So what I have just done is I completed x squared plus 2x plus 1 as a perfect squared trinomial, which is equivalent to x plus 1 squared. And the entire denominator is of the form x plus 1 squared plus 4. So it takes the form a squared plus u squared. And we know that it will yield the inverse tangent function. So for the first two, I'm factoring 1 over 10. So that will be 4 ln of absolute value of x plus 3 ln of the absolute value of x squared plus 2x plus 5. Okay? Then minus 12 over 5, 1 over a or 1 half, arctangent of x plus 1 all over 2 plus c. So 1 over 10, 4 ln x plus 3 ln x squared plus 2x plus 5 is actually equal to x raised to 4, x squared plus 2x plus 5 raised to 3, minus 12 over 5 times 1 half is 6 fifths. 6 fifths arctangent of x plus 1 over 2 plus c. One final example. We evaluate the integral of three minus x plus x squared all over x squared plus 1 x squared plus 4 dx. So what we have here in the denominator are two distinct quadratic factors. So let us write the integrand as a all over, or rather a times, we take on the derivative of x squared plus 1, which is 2x, plus another constant b over x squared plus 1, and then plus another partial fraction for x squared plus 4, that will be c times the derivative of x squared plus 4 is also 2x, plus another constant b all over x squared plus 4 quantity dx. So you should write this as the integral of, or a times the integral of 2x dx over x squared plus 1 plus b integral of dx over x squared plus 1 plus c times the integral of 2x dx over x squared plus 4 and d times the integral of dx over x squared plus 4. Okay, so once we know the values of a, b, c, and d, we just proceed with the integration. So you verify the following values. No? For a, it should be equal to 1, b should be equal to negative 1 half, c is 1. Oops, sorry, I think I have the wrong set of values. Your a should be negative 1 over 6, b should be equal to 2/3, c is 1 over 6, and d is 1 over 3. Okay, so you can verify these values. So let us plug in those values. Negative 1 over 6, 2x dx over x squared plus 1, and then 2/3 dx over x squared plus 1, c is 1 over 6, 2x dx over x squared plus 4, and d is 1/3 dx over x squared plus 4. So we integrate. The 2x dx over x squared plus 1 is ln of x squared plus 1 plus 2/3. Dx over x squared plus 1 is du over a squared plus u squared, 1 over 1 arctangent of x over 1, plus 1 over 6, 2x over x squared plus 4 is ln of, that will be ln of x squared plus 4 plus 1/3. Dx over x squared plus 4 is du over u squared plus a squared, or 1 over 2 arctangent of x over 2 plus c. Let us factor 1 over 6 between ln x, negative 1/6 ln x squared plus 1 and 1/6 ln of x squared plus 4. So that will be ln of x squared plus 4 all over, because the first ln is preceded by a negative sign. So over x squared plus 1. and then 2/3 arctangent of x and 1/6 arctangent of x over 2 plus c. Okay? As an exercise, you work on the following integral.